Okay, I see the numbers starting to level off, so we'll go ahead and get started. Hello, everybody, and welcome to the Maria Mitchell Association Summer Science Speaker Series. I'm Dr. Regina Jorgensen, the director of the Maria Mitchell Observatory, and I'd like to thank you for tuning in tonight for a very, very special event and a special speaker. I'm going to start off by quickly thanking our sponsors for tonight's event, Bank of America, Cape Air, the White Elephant, and Cisco Brewers. And thank you to their support for we're able to do these kinds of things and keep them free for everyone to attend. And we'll have a couple more science speaker series Wednesdays at 7 p.m. through the end of August. Before we begin, I'll just also make the note that I always do, which is we encourage you to ask questions. We'll take all of the questions at the end of the talk tonight. So if you have any questions at any time, feel free to put them into the Q&A function, which you should find down at the bottom of your screen. And we will get to all of the questions at the end. So tonight it is my really great pleasure to introduce Jorge Stolle-McAllister. Jorge is the Maria Mitchell Association Post-Baccalaureate Research Fellow, which is a position sponsored by the National Science Foundation and the Maria Mitchell Association. And she is part of the Fast and Fortunate for Frb follow-up collaboration, or F to the 4. This is an international collaboration of astronomers who are using fast radio bursts, and George is going to spend a lot of time tonight explaining what those words mean to map the contents of our universe. Georgia began her time here at the Maria Mitchell Association actually as an NSF-sponsored REU, which is Research Experience for Undergraduates intern in the summer of 2019. And she was a frequent user of our Loynes 24-inch telescope and ended up turning her summer project into a year-long thesis project back at her home institution, Kenyon College. In the spring of 2020, Georgia earned the highest honors defending her senior thesis, which was titled Learning from Star Shadows, Investigating an Eclipsing Binary Star. And I'll just point out that the Kenyon College Physics Department senior thesis process is extremely rigorous. It involves not only a written thesis, but also an oral thesis defense in front of a committee of astronomers from outside of Kenyon College. So it's very similar in spirit actually to a PhD dissertation defense. So this is really quite an honor. Georgia received her bachelor's of science degree in physics from Kenyon College in the spring of 2020, and then moved back to Nantucket and to the Maria Mitchell Association in September of 2020. And she has been performing research here with us for the last year as part of the F4 collaboration. That's what she's going to be speaking about tonight. And most recently, she has also been helping to mentor our new crop of REU interns, this summer's 2021 cohort. In addition to all of her scientific achievements, Georgia is fluent in both Spanish and Russian, and she actually initiated and ran the Maria Mitchell Association's first ever Spanish language open nights, which we held virtually due to the pandemic this past year. So we have been just extremely delighted to have Georgia with us this past year and grateful to her for everything that she has done and contributed both in terms of research and in terms of outreach here at the Maria Mitchell Association. And so I'm extremely excited to welcome her here tonight to actually speak to you all about our research. And with that, I will stop my screen share and turn it over to Georgia.
Thanks so much. I will share my screen now and hopefully this, yep, okay. All right, well, thank you so much, Regina. I'm really excited to get to tell you all about fast radio bursts and the things that I've been working on. I think it's super cool, so I hope you will too. Before I get started on that, I also wanted to just tell you a little bit about the group that I've been working with. If I can change the slide. The group that I've been working with, Regina also introduced, was the Fast and Fortunate for FRB Follow-Up, or F4 collaboration. And this is an international collaboration. We have people from UC Santa Cruz in California, the Maria Mitchell Observatory, obviously. We have people from Chile, Northwestern University, and in Denmark. So it's really an international collaboration, and it's a lot of fun to work with everyone. And it's been a really great team to be a part of. So now I'm going to tell you what the 3 mysteries that I want to tell you about today. So there's 3 stories here, and they're all kind of intertwined, but they kind of break out into one, what are fast radio bursts? What are they? Why do we care about them? Why are they interesting? Peritons, which are these mysterious, potentially FRB signals coming from Earth. So we'll talk about that mystery. And then the big question is this mystery of the missing matter in the universe and where it's hiding and how we're going to try to find it. So to start off, I'll introduce the main character, of course, of the talk, which is the fast radio burst, or FRB. And these are just really extremely bright flashes of light in radio wavelengths. So they're so fast, they take about a thousandth of a second, which is 100 times faster than you can blink your eyes. So that's a very small amount of time to have so much energy come and be released, because the amount of energy that they release in just those few milliseconds from one fast radio burst is about the same amount of energy, sort of more or less, if you were to flash on and off 1 billion suns all at once. So that's a lot of energy to cram into that little amount of time also. And then they're radio bursts because we detect them in radio wavelengths. So it's light, but it's in radio wavelengths. So just a quick either review or an introduction to light. This is we also call the electromagnetic spectrum. And we have, there's a huge range of light wavelengths. We only see a teeny tiny bit of it. We only see visible light, which is kind of enlarged here at the bottom, but it's really this tiny little sliver of the whole spectrum. We can't, with our eyes, we can't see light in any other wavelengths, but we have instruments that can. And so we can learn a lot about things from light in other wavelengths. And today, at least for the first part here, we're obviously talking about radio waves, which is what fast radio bursts are light in this regime. So with these long wavelengths. And we detect them using radio telescopes. So some of these might look sort of familiar, like the Parkes telescope and the Green Bank telescope. These are, single dish radio telescopes. The Arecibo telescope is also a single dish. You might have heard about it in the news this last year. It actually collapsed, which was very sad. It's done a lot of good science. And then we also have other kinds of radio telescopes, which are in arrays. So these are like sets of smaller radio dishes that you can kind of spread out, and many of them you can move around into different configurations, and you get like an even bigger radio telescope made of all these ones together. So these are like the Very Large Array, which is actually the real name of this radio telescope, is the Very Large Array. And then there's the Australian Square Kilometre Array in Australia. And these are both really good at detecting fast radio bursts and finding out exactly where they come from, which we'll talk about later. And then there's one more on here, which is a strange looking one. This is the Canadian Hydrogen Intensity Mapping Experiment, or we just call it CHIME because that's way too long of a name. And this is in Canada, and it's a funny looking telescope, but it is great at detecting fast radio bursts. It actually detects the most fast radio bursts out of any other telescope. And so from CHIME, we know more now about the population of FRBs. So they're kind of a mysterious thing, right? There's so much energy coming from them, such a short amount of time. There's a lot of mysteries there, but I'm going to tell you first what we do know about them, and then we'll go on to what we don't know. So what we do know about FRBs is that they are coming from everywhere in the sky. They're spread out all over the sky. They're not concentrated in any one particular direction. And there's a lot of them. So CHIME in 1 year detected over 500 of them, and that's because they have a really wide field of view. They can look at a lot of the sky at once. But of course, we can't see the whole sky all at once, all the time. So we miss a lot of them. We think there's probably up to about 1,000 FRBs happening every day, but we only see a small fraction of those. And they're coming from everywhere. We also know that they are coming from, almost all of them are coming from outside our own galaxy. So there's only been one fast radio burst that was detected coming from within the Milky Way, within our own galaxy, and everything else, all the other ones have been way, way further away. So from galaxies that are much more distant. This makes them harder to study, right? Further away things are harder to see and learn about, but it also makes them very interesting objects to look at and learn from. The other thing we know about FRBs that makes them curious is that some of them repeat. So they have multiple flashes from the same, the same place. And some of them don't repeat, at least not as far as we know. So there's one FRB that's a repeating one that repeats about every 16 days. It has a whole bunch of flashes and then it goes quiet for 16 days and then it does it some more. But most of the vast majority of the FRBs we've detected so far, we've only seen one burst from them. It could be they're going to repeat later. It's just going to be it's going to be way in the future, or we could have missed it. But most of them we only see one burst from. I think there's only like maybe 30-ish or so that are repeating ones, and all the rest, several thousand, are not repeating ones. So this also adds to the mystery of what we don't know about FRBs, is what causes them. We've got these amazing events that are releasing so much energy, but we don't know how they're releasing that much energy or what's making that happen. There are lots of theories about it though. And there's more than 50 theories for what causes fast radio bursts. And the ones I chose here, I chose purely based on the name. I don't know what most of these are, but they're wonderful names. Like an axion quark nugget. I don't know what that is, but it sounds great. Annihilating mini black holes. I feel like that could be like the name of a carnival ride or something. Strange star crust. Yeah, so these are, I don't know what most of these are, and people are working on these and coming up with this. This takes a lot of imagination to come up with these things, a lot of creativity to figure out how this could work. And a lot of them are fairly, speculative, very theoretical. They don't have a lot of evidence, at least not yet, to back them up. But it's good to come up with options and ideas. The most probable cause, I'm just going to tell you, right? So it is a mystery. We still aren't sure, but the most probable cause of FRBs are magnetars. And there's the most evidence for this being the progenitor of FRBs, the thing that causes them. And so magnetars are these super, super dense remnants of dead stars. So when really large stars end their life, some of them leave behind magnetars. And these are, besides being just crazy dense, they also have an unimaginably large magnetic field, strong magnetic field. So their magnetic field is 1,000 trillion times stronger than the magnetic field of the Earth. So we have a magnetic field on the Earth. That's what makes your compass point north, and it protects us from things in space as well. But a magnetar's magnetic field is just crazily strong. If you got within like somewhere around like 600 miles away from a magnetar, the magnetic field is strong enough that it starts to pull your atoms apart. It pulls your electrons and protons apart from each other. And so you just kind of dissolve from an atomic level, which I can't imagine would be very pleasant. So I would stay away from magnetars if I were you, but they're really far away, so it would be hard to get that close to them anyway. Okay, so we have this guess of magnetars, but even if we don't know for sure what causes them, we can still use fast radio bursts to learn about other things. So we're going to talk about that, but for the rest, basically the rest of the evening. But first, I'm going to tell you how FRBs were discovered, because they are these amazing events but they actually were discovered fairly recently. They've probably been happening for forever, we just never noticed them. So the first FRB that was detected arrived on Earth in 2001, and it got to the Parkes telescope in Australia, and nobody noticed it. It just got recorded in the data, and because no one was looking for it. Nobody knew these things existed. They weren't looking for this kind of signal, and there's a lot of data that comes into a telescope. So it sat in the archives, in the data. It was saved for 6 years. 6 years later, there were some scientists, Duncan Lorimer and his student David Narkovic, who were going through archival data from the Parkes telescope, and they were apparently going through data from 2001, and they came across this signal that they weren't looking for FRBs, but they came across one. And this was a great discovery. This is the plot of what an FRB signal kind of looks like if you plot it with frequency versus time. So I'm going to tell you more about this plot because this is like the famous one for the discovery of FRBs. And this tells us why FRBs are so special and why we like them so much. It's because they have this unique feature where the higher frequency wavelengths of light get to the telescope first, whereas the lower frequency wavelengths get in a little bit later. So they're kind of spread out. These are still all radio wavelengths, but even among radio wavelengths, there's a range. Yeah, there's a variation in frequencies. So the short wavelengths, which is a high frequency, gets here first. The longer wavelengths, which is a low frequency, gets in last. And it makes that curved kind of shape in a graph like this. And this is caused, so this time delay that happens is because the radio waves are passing through stuff, where they're traveling through lots of space to get to us. And by the time they get here, they've crashed into lots of particles and things all along the way. And the higher frequency wavelengths have more energy, and they just kind of shove right through all that stuff, keep going fast and get to us first. The lower frequency wavelengths have more of a hard time of it. They kind of get stuck, they crash into these things more, they interact more, and they're delayed. And so they get to us later. And so this is super helpful because the stuff that they're crashing into is stuff we can't see. But because we can see how that time difference happens, we can then learn about the stuff that they crashed into on the way, even though we can't see it. So this is going to help us solve our main mystery of the night, which is, where is all the missing matter? We've lost some matter. So you might have heard of this sort of division of energy in the universe before into dark matter and dark energy, and these are things we don't know much about either. Most of the universe we don't know much about at all, but we're not actually talking about that at all today. Though that's a whole different topic. We're only talking about ordinary matter, which makes up about 5% of the universe, which is a very small sliver. But this is everything that we can see and basically everything we know really anything about. So this is electrons and protons. This is what makes up people, planets, plants, stars, black holes. Everything that we really know much about is made up of ordinary matter, made up of protons, electrons, neutrons. And it turns out that half of this stuff is missing also. So we only know about 5% of the stuff in our universe, but we don't even know about half of it. So we think there should be, we know there should be this certain amount, but we only actually, if we look out into space, we can only really account for half of it. So if you can sort of count up, measure matter that you can see in galaxies, it really only adds up to about half of what we're expecting. So half of the other stuff we can't see, and we think it's out there, but we don't have really very good evidence for where. And we have this idea of how the universe is kind of constructed. So and we call it the cosmic web. So this is a beautiful picture. This is a computer simulation of how matter clumps together in the universe. So the brighter places are where there's more matter, denser, clumped more together. And so where it's really bright, those are things like galaxies that we can see that emit light, and we can observe them with telescopes, and we can see that they're there. But the rest of the stuff that's kind of more purple, darker colored, that part is really like filmy, really diffuse and hard to see because of that. It's not glowing really brightly or anything. So we think that's where the missing matter is, but we don't have a good way of actually looking for it. But FRBs have to travel through all this missing matter. They have to travel through the cosmic web to get to us from their faraway galaxy. And so they crash into this matter as they come along. And this helps us know that it's there because of that dispersion measure that we talked about, right? Where some of the wavelengths are getting delayed and some of them keep going through and get here first. And that delay tells us that it's the FRB is interacting with stuff along the way. So this is going to help us. This is going to help us find the missing matter. But in order to actually make a good measurement of this and be very sure of anything that we're measuring in terms of the amount of this matter, we need to know a couple of things first. We need to know, for one, we need to know the distance to the fast radio burst, because we want to know like the density of stuff in between, and we can know how much stuff is in between, but then we need to know from the dispersion measure, but then we need to know the distance to the fast radio burst in order to get more of a density measurement. So that's one thing we need to know. The other thing we need to be able to do is like identify and split up the dispersion measures from different parts of the universe that the fast radio burst is going through. So it has to travel through its own host galaxy, right? Its own galaxy first in order to get out into intergalactic space. And then when it gets to us, it also travels through the Milky Way. So some of the dispersion that we see, some of that spreading out, the delay of the light is coming from things in our Milky Way or in the other galaxy that is a little bit more dense, and that is also adding to the dispersion. But we don't really care about that so much. So we want to know about that in order to sort of just subtract it off and just focus on the stuff in the intergalactic medium, because that's where the missing matter is, right? We can see the matter in our galaxy and in other galaxies, but we can't see this stuff in between. So we want to know how much of the dispersion that we see in the FRB is actually coming from the stuff in between galaxies. In order to do that, we need to study the host galaxy, because we can have models for our own galaxy, figure out how much that contributed. But in order to then also get an estimate for the host galaxy, we need to study that. And in order to study the host galaxy, it's a whole long chain here, right? In order to study the host galaxy, we have to actually know where the host galaxy is. And this is hard. This is tricky, because so telescopes that are single dish telescopes that are observing fast radio bursts are not always great at knowing exactly where in the sky that came from. So the Arecibo telescope detected this a fast radio burst, and this yellow circle is kind of showing the area on the sky that it knew the FRB was coming from, somewhere in there. And then the picture behind is not a radio telescope picture at all. That's a Hubble image, but just like layered behind it to show you that there's a lot of galaxies in that area. So how are we ever going to find which particular galaxy the FRB came from if our radio telescope detection just tells us, it's over there, more or less, but we want to know exactly which galaxy it came from. Luckily, other telescopes are better at this. So arrays are what can do this better. Arrays of telescopes where you have multiple telescopes. So the Very Large Array and also the Australian Array are both really good at this localizing game. And so you can see this on the right, there's now a tiny little yellow circle in there, and that's the localization from the Very Large Array that said, okay, the fast radio burst came from inside this tiny little circle. And now we have a much better chance of figuring out which particular galaxy the fast radio burst came from. It narrowed it down a whole lot for us. This is tricky though. Most of the vast majority of the FRBs that are detected, we don't have a good localization for. So CHIME, right, which was the funny looking telescope that is really good at detecting FRBs. It detects lots and lots of them all the time, but it's not very good at knowing exactly in the sky, where in the sky they came from. So there's only about like 15-ish FRBs that have a very good localization and know where they're coming from. All the other ones are just, they happen, they're there. We can still use them for great learning more things, but we can't figure out which particular galaxy they came from yet. And the repeating ones are easier to do this for because you get lots of chances, right? They flash multiple times. You can look at them with your arrays and have a better, you get more chances to figure out exactly, to pinpoint where it came from. But most FRBs are only single burst, one repeater. You get one shot to see where it came from. And ASCAP, the Australian array, is really good, is getting really good at doing that, even with just single bursts. So that's good news. And once we're able to get this localization, we can study the host galaxy. But before we move on to that part, before we get to, we're going to kind of move away from radio observations in a minute and go on to other kinds of telescopes and observations. So before we do that, I want to tell you a funny story that I like about radio observations. So shortly after, so this is again the Parkes telescope in Australia. Shortly after the first FRB was discovered, people were looking for more of them, looking through archival data, looking through new data, and they started finding these signals that looked a lot like FRBs, right? It has this same sweep like the FRB has, but these are coming from Earth, which is a problem. We don't care about the things so much that are coming from Earth because we want to know about the FRB that's far away in space, right? That can tell us about all the stuff that it passed through on the way here. But these tricky signals from Earth that look like FRBs were kind of throwing everything off. And these are called Peritons. There's a couple of ways of telling them apart from FRBs, but they were definitely casting doubt on whether FRBs were even real and from space. So Periton is kind of a funny name. And I don't know who named this phenomenon object a Periton, but a Periton is also a mythical creature. It's part stag and part bird. And the story goes that it lived on Atlantis in the mountains, but it escaped. It flew away before Atlantis sank, disappeared. And this strange creature, it's sort of said to be kind of greenish bluish, and said to go. It went and lived in Greece, perhaps, and Rome. But it has the body of a stag and the wings of a bird, but it casts the shadow of a human. So it's just a very kind of strange creature. And it was described in a book called The Book of Imaginary Beings, which was co-written by Jorge Luis Borges. And many people think that he invented this creature because in his book, he's got lots and lots of imaginary creatures that he describes and tells their stories. And he claims that the Periton description came from a lost medieval manuscript, except no one's ever been able to find that lost medieval manuscript. And so most people think that he invented it himself. Jorge Luis Borges is a very interesting person. Also, he is an Argentinian author in the 20th century. He was educated mostly in Switzerland, though, and he grew up speaking Spanish and English, but he actually could read in English before he could read in Spanish. He also then taught himself German and Old Norse, which is an interesting choice. But he sort of invented his own genre of writing and won lots of prizes, and kind of is very well known for he He wrote prose and poetry. He was just an interesting guy, and he perhaps invented the Periton, which then got adopted as the name for these mysterious FRB-like signals. So we're going to go back to Peritons in Australia. The Peritons in Australia, since they're coming from Earth, there's some kind of what's called radio frequency interference. So radio telescopes have a really hard time because we use radio waves all the time. Cell phones, televisions, navigation systems, computers, radios, everything technology-wise that we use is often operating in radio wavelengths. And so the telescopes can see all this, right? They're sensitive enough to pick up these really faint signals from far away in space. So they can definitely pick up these signals on Earth. And it gets in the way of the actual science part that we try to do with radio telescopes. A lot of these, we know exactly what frequency they're at, and we can try to mask them out and get rid of them. But the Peritons were happening, they were kind of unusual. They weren't like any other kind of radio frequency interference that people had were used to, trying to mask out and get rid of. So there were lots of questions of what could it be. They're really annoying. Could be some kind of a hardware failure on site, some weird sort of lightning. Lightning also causes radio frequency interference. Some sort of solar phenomenon that nobody knew about. Airplanes, navigation systems. People didn't know. But they did lots of tests, and the final clue that clued everyone in was by detecting plotting the time of day that they were detected. And so FRBs, you can see, are kind of detected basically all day long, any time of day. And there weren't a whole lot of them at this point to compare to, but the Peritons are all clustered. You can see they're all smushed together here, and they're clustered around lunchtime in Australia. So this was what gave it away. Astrophysical objects do not care about lunchtime in Australia. But Peritons, it turns out, were microwaves. So people on site were microwaving their lunch, and this was creating radio waves that were getting picked up by the radio telescope. And they did this whole test. There's a whole paper written on how they figured out what Peritons were and the test they did to confirm it. So they did this whole test where they were putting a mug of water into the microwaves and then turning it on for a certain amount of time and marking very precisely what time they did this, and then looking through their radio data and seeing if they could match it to a Periton. And at first they couldn't, it didn't show up. But it's because it only shows up if you open the microwave door before it's done running, before it has turned off. And if you open the microwave door before it's turned off, that releases some radio waves that make this Periton signal. And so it was very clear then that the Peritons were definitely not FRBs. So this gave all the credit back to fast radio bursts as being real things, really from space. They are not microwaves. And so we can go back to believing them and using them as tools to study space. Okay, so we solved that mystery. The Periton mystery is resolved, but we're going to go back to our missing matter mystery. This problem where half of the matter that we think should be there doesn't really seem to be there. And in order to find it, we need these certain things, right? We need the distance, the FRB, and we need to separate out these dispersion measures, which means we need to study the host galaxy. So if we've localized the host galaxy, right, we've got the radio, used the radio telescopes, the arrays, to localize exactly where in the sky the fast radio burst came from. We can find which galaxy it came from, and then we can look at that galaxy with other telescopes. So these are all optical telescopes that are really ginormous. They're all on Earth also, well, except they're not all on Earth, sorry. The radio telescopes are all on Earth, but the optical ones are not. So the Hubble Space Telescope is in space. The Keck Observatory is in Hawaii. The Gemini Observatories, one of them is in Hawaii and one of them is in Chile. And then the SOAR telescope and the Very Large Telescope, again, yes, that is actually the official name, Very Large Telescope. Those are also both in Chile. So these big optical telescopes, with these, we're going to look at the galaxy where the FRB came from. So we're not looking at the fast radio burst itself anymore, but just at the galaxy. And just, yeah, so just to confirm, reiterate that these are now visible light. We're no longer looking at radio wavelengths. We're looking in visible light now with these big telescopes. So as an example of what this kind of looks like, of doing follow-up observations, we have the localization from the radio telescope. So that's what these blue circles are. The radio telescopes are good enough to say the fast radio burst came from inside this tiny circle somewhere. And then we can look at that part of the sky with, in this case, the Hubble Space Telescope, and take these really cool images and see where in particular inside the galaxy the fast radio burst is coming from. And I chose this particular example because it was done by one of the people in the F4 group. Her name is Alexandra Mannings, and she's at UC Santa Cruz. And this was super exciting and new work. So it actually got picked up by lots of press. There's CNN had an article on it, CBS, Science News, NASA, space.com. There's all kinds of news articles on this, which was really exciting. So you should go find them and read them, because this was a really cool discovery and has a lot of interesting conclusions coming from it and interesting next things to study as well. But I'm not going to go into all the details of those. So you should, there's lots to read on it. So you should go learn about this too, because this is also really, really cool stuff. Okay, so this is one example. The other example that I'm going to talk about more is, because this is the data that I've been working with this year. So this is an image from the Very Large Telescope. The one on the left is like the whole field of view that it can see. And then the one on the right is zoomed in onto just the host galaxy of the fast radio burst. So the FRB came from inside that tiny little orange circle. And we're not looking at the radio burst anymore. It happened in 2018. It's gone, it's done. But we're looking at the galaxy that it came from. And you might have been expecting beautiful images of galaxies, but this galaxy is really far away. And so we get to see a smudge. Even with this huge telescope, it's still kind of a blurry smudge. But we're going to learn so much from this blurry smudge. It's great. Let me tell you first about the Very Large Telescope. Wonderfully creative name. This is a telescope in Chile. It's in the Atacama Desert. And so these kinds of telescopes, you want to have them up really high. It's on a mountain in the desert. So up really high and in really dry air. So it's perfect because the atmosphere gets in the way of observations. It makes things blurry. And this is a huge telescope. So there's 4 of them actually up there. But each one, the mirror it's an 8-meter telescope. So the mirror of the telescope is 8 meters across in diameter. That means you could put like 3 really tall people, like really tall basketball players or something, really tall people end to end, lay them across the mirror, and that would kind of measure the diameter of the mirror. This is a really big telescope, and this means it can collect lots of light and see things that are really dim and really far away. And then we can put different instruments on the back of the telescope depending on what in particular we want to measure or learn about, that have kind of different properties, different ways of working. So the one in particular that is the data that I've been using is called the Multi-Unit Spectroscopic Explorer, or MUSE for short. And I think it's amazing. Like, it looks like some kind of spaghetti monster or like science fiction contraption. But this is real. This is a super cool instrument. You can see it mounted on the telescope over on the right. It's like kind of below, and the telescope's looking up out of the slit. And this is a spectrograph. So it's doing spectroscopy. So we're going to talk about spectroscopy now for a little bit, because this is a very useful tool in astronomy that we use all the time, and it's really interesting. So spectroscopy is when you're studying light, that you spread out light and study it based on its component wavelengths. So if you've ever gotten to play with prisms, where you can shine white light through a prism and then it makes a rainbow on the other side, or if you've just seen a rainbow when it rains and then the sun shines through it, the sun is, like you have to be at the right angle, the sun is coming through the water droplets, and that's acting like a prism and spreading the light out into its colors. And then we can look at those colors and learn things from them. So what can we learn from them, right? Why do we even want to use spectroscopy? Well, because remember this smudge galaxy, this really blurry, dim galaxy? Well, if we use spectroscopy, we can learn so much about it. We can learn how far away this galaxy is. We can figure out how it's moving. We can learn what elements are in it, how stars are forming in it, whether or not it has an active black hole. We can just get so much about this little smudge galaxy if we use spectroscopy. So the main way that we can do this, that spectroscopy really works, is that elements all have their own particular emission so the way atoms work is that they give off light in only very particular wavelengths. So if you have a hot gas of some kind of atom and it's giving off light and you put that light through a prism, it will separate out into and show you only very specific wavelengths. And the same goes the other way. If a cloud of gas is absorbing light, it also only absorbs them at very particular wavelengths. And the column all the way over on the right is just another way of looking at spectra. So the pointy parts, right? The spikes are where at a very particular wavelength that then is brighter at that particular wavelength, depending on what element is emitting the light or absorbing the light. We're mostly talking about emission today. And every single element has its own spectrum. It has its own fingerprint. And this is great because we can then study these fingerprints in a lab beforehand, figure out exactly what pattern each element has, and then we go look at stuff in space, put it through our prism, and we can be like, okay, what pattern? What patterns are in here? Can we match it? Which elements can we match it to? And figure out what elements are in things in space that way. Actually, helium was first discovered in the sun, which is why it's called helium, because someone was looking at starlight through a spectrum and found a pattern that they hadn't found on Earth. And so they thought, well, this is just an element that's only in the sun. Turns out it's also on Earth, but they discovered it through spectroscopy. So that's pretty cool. All right, this part I'm going to fly through. So if you want to know more about it, I'm happy to tell you, but I just want to tell you really quick that we have these two tricks that we use to help us make use of these spectroscopy fingerprints. So one is the Doppler effect. This is the effect where light that is moving towards you gets blue shifted. So the wavelength gets kind of squished, and that squishing makes it look bluer. Okay, so that's blue shifted if it's moving towards you. If it's moving away from you, the opposite happens. The light gets kind of stretched out, has a longer wavelength, and that we call red shifted. So that's Doppler effect. The other thing that this is a whole topic in and of itself is Hubble expansion, so the universe is expanding, and it's expanding in a way that the galaxies that are further away from us are moving away from us faster. And the galaxies that are closer to us are moving away from us slower. They're still moving away, but not as fast. So between these two, we can look at we can look at galaxies, see how much their light is redshifted. And if it's really redshifted, so it's moving away really fast, we can also then say it's really far away from us. So those are the tricks we use. And that's why this spectroscopy game works. because we can take an element measured in the laboratory, find the fingerprint pattern. This is the little bottom row on this picture. See that really like where those black lines are? They're separated by very particular amounts, and they're always going to be separated by those amounts. But then if we go look at a nearby galaxy that's moving away from us kind of slowly, those lines are shifted a little bit over more towards the red part, right? If you go to even further away galaxies that are moving away from us faster, that pattern of lines gets shifted even more to the red part. So you can look at light from a distant galaxy and find the pattern of a certain element and say, well, I know it should be at these wavelengths in the laboratory, but I see this same pattern shifted all the way over to these longer wavelengths. So I can say, I know how far away it is now. So this is great because this solves one of the problems. This is what we were trying to do, right? We wanted to know the distance to the fast radio burst. So if we have the host galaxy, right, we localize that, and then we're going to use spectroscopy. So we find a fingerprint of an atom from the light that's being emitted from that galaxy. We see how much it was redshifted, which tells us how fast it's moving away, which tells us how far away it is. So this is great. We've got the distance to the fast radio burst. Now, we still need to do this dispersion measure, separating out. So we want to only know about this intergalactic medium part, which means we need to know about the host galaxy part in order to be able to subtract that out. So we're going to study the host galaxy more closely because we want to know more about it. So we've got the distance, but we want to figure out like what it's made out of, how many stars it's forming, how it's moving or rotating, because this is going to help us. Figure out that dispersion contribution from the host galaxy. And this is where the MUSE instrument comes back in. So remember this spaghetti monster instrument on the Very Large Telescope? This is called an integral field spectrograph. And these are so cool. These are super awesome because they take an image of something, but every single pixel in the image is also a spectrum. So normally when you do spectroscopy, you get one spectrum for the whole galaxy. This way you get a spectrum for every pixel in an image of the galaxy. And this is amazing because now we can figure out that different parts of the galaxy have, sort of different amounts of elements, different things happening in them, and we can make cool maps. So, well, first let me tell you, so you can just as an example, you can see like right in the center of the galaxy in this spectrum where we have this is where atoms are emitting light at a very particular wavelength. Well, there's way more light being emitted right at those particular wavelengths in the very middle of the galaxy than there are over on the edges where those lines are a little bit weaker and shorter. Right, so if we can do this we have this information for every single pixel, we can make maps of the galaxy. So this kind of map is looking at a particular element and seeing how much light it's emitting. And this then also we can convert this into a star formation rate. So we can tell how fast stars are forming, like what rate stars are forming in the galaxy based on the amount of light of certain elements. And so you can make a map like this where you can see that in the center it's brighter in this particular element. And so we know there's more stars forming there. Whereas out on the edges, it's not as bright, there are fewer stars forming there. And this makes sense, this is reasonable. And this just to show you again, the circle where the Frbs was located to. So the other reason that these maps are really interesting and helpful is that they can tell us if something weird is happening at the Frb location, right? Because then that might help sort of solve the mystery of what causes them as well, if we can find weird things happening in the galaxy where the Frb came from. But mostly we're using them for this dispersion separation thing. So here's the other kind of map that I'm going to show you today, which is a velocity map. So remember the blue shift and red shift that we talked about? Well, since we have a spectrum for every single pixel, we can do this for every pixel and say, well, these parts of the galaxy, the blue parts, are moving towards us, whereas the red parts are moving away, because of how much their spectrum was redshifted or blue shifted. And this tells us that the galaxy is rotating. It tells us that that blue part, you can think of it flipping towards you, and the red part is sort of flipping away from you. So that galaxy is spinning and rotating in this direction. So that's pretty cool that we can learn. We can learn all that from spectroscopy, and we can make these kinds of maps because of the special feature of the Muse spectrograph, where every pixel has a spectrum. So great. So we learned about the host galaxy, which means we can have a good estimate of how much stuff the FRB passed through as it was getting out of its own galaxy, right? And we've got models for the Milky Way, but that's closer, that's easier to study. So now we've got actually how much of that dispersion measure, how much of that sweep that we saw of light getting spread out as it travels to us, right, of the longer wavelengths arriving later, how much of that was actually due to the intergalactic stuff, as opposed to the galaxy stuff. And this is what helps us with this question, right? Our mystery of the missing matter. Where is that half of it? Well, remember, the FRB is crashing into that as it goes, and now we have the things we need. We have the distance, we have the dispersion, and we can calculate the density of the matter in this part, which means we actually found it. We solved it. We thought it was there, but we have evidence now that it's there. The missing matter is spread out in between galaxies. And this dispersion of the FRB is what tells us that. So that's amazing. That mystery is fairly well solved. We've got good evidence, and that it's in between galaxies. But that means that matter is really, really diffuse. So just to give you these are hard to think about numbers, but in an average room size in space in between galaxies, you only have 1 or 2 atoms, which is like nothing. Inside a galaxy between stars, you maybe have 1 atom per cubic centimeter. So per the size of like a sugar cube, you get 1 atom. And then if you think about intergalactic, that's even fewer. So this is like hardly anything. So to just give you a comparison of more normal things, breathable air, like air that we're breathing all the time, has more, like on average, more or less 10 billion atoms per cubic centimeter. So 10 billion times more atoms in a cubic centimeter than the interstellar medium, and way more than intergalactic medium. And then a person has about 7 billion atoms. So that's 10 with, that's 1 with 27 zeros after it. That's a lot of atoms. And if you just think about how much space you would need to spread out all of the atoms, say, that makes up a person, how much space you need if you're going to spread them out so that they're at this intergalactic medium density, so that they're spread out to only have 1 or 2 in every like room size. That's a lot of space. Oh, real quick, I also wanted to point out that this image in the background that I'm using as an illustration, was taken by one of the REU interns this summer out at the Loynes telescope. So this is a beautiful image of the Black Eye galaxy. And you should come back to the Science Speaker Talks next week to hear all of their cool projects. But this is just a really pretty image that I'm using as an illustration. So thank you for that. Okay, so like I said, it's spread out so thinly in intergalactic space, but I think that Douglas Adams from The Hitchhiker's Guide to the Galaxy puts it very well, in that you just won't believe how vastly, hugely, mind-bogglingly big space is. So that really diffuse missing matter adds up. And actually most of the matter that the FRB travels through is in that intergalactic space. Only a small fraction of it actually comes from the galaxies on either end. So we found the missing matter, but now we actually want to know how it's spread out. So if you take an FRB that happens to be like behind a more dense region, right? Like this middle line here. You get a higher dispersion measure, and you can say, okay, there's more stuff in this direction. whereas the other two lines go through more kind of empty-ish looking spaces. And so there's less stuff over there. Because we want to be able to, we have this simulation of the universe and of how matter is spread out, but we want to be able to measure it too. In order to do that, we need so many more FRBs, and we need to do the whole process. So the whole process of detecting the FRB with the radio telescope and localizing it to a host galaxy and measuring the distance to the host galaxy and figuring out the dispersion from the galaxy versus the intergalactic medium. So we got to do that whole process for lots and lots of FRBs in order to try to make this map of the cosmic web. But this is going to be so cool because we're trying to map how the universe is structured, how matter is spread out in the universe. And that's a pretty amazing goal to have and a really fun thing to think about and to study. And it's just so cool to me that FRBs, which are kind of a mystery of their own, can help us do this, even without knowing exactly what they are. With what they are themselves, they can help us try to solve this even bigger mystery. So I'm going to leave you with just, if you don't remember most of what I said tonight, that's okay. But I'm leaving with 2 points, which I hope you will remember. One is that just what fast radio bursts are, and that they're extremely bright, short time flashes of light in radio wavelengths coming from faraway galaxies. We're not really sure what causes them, but probably magnetars. And the other point is that the way the fast radio burst slows down and gets delayed as it travels through stuff in the universe, as it comes to us, that can tell us about stuff that we can't see, about the matter that we can't see in the universe, just from the signal that's left behind from the FRB. So those are my 2 points. And then, because as Mariah Mitchell herself said, science is somewhat beauty and poetry, I'm leaving you also with a poem by Jorge Luis Borges, who was the inventor of the Periton mythical creature. And I thought this one was sort of astronomy themed, so it would be relevant. Okay, and I hope you will have questions. I would love to try to answer any of your questions.
Yay, Georgia, that was awesome. That was so inspiring and so funny as well. That was really, I think, one of our more humorous science talks of the summer. So congratulations, this is really awesome. We have a couple comments in the chat. I just like, if anybody has questions, feel free to pop them in the Q&A right now. We have some great jobs, and also one note that Alex Mannings, who you mentioned, who has done the Hubble images, was also an
MMO intern. Yeah, I forgot to say that. Yeah, and now she's in the F4 collaboration as well.
That's right. Let's see if we have any questions. Well, I'm going to really quickly ask you while we're waiting for anyone. I just did a quick calculation because this was the first time I saw your estimate of the number of atoms in a person, and then thinking about how long you would have to stretch those out.
Stretch it out.
So if you assume so I was thinking like how, if you stretched out all the atoms in a person, how far would it be? In the density of the intergalactic medium, which is like 1, really 2 atoms. Yeah. Did you work? Because I just did like a quick estimation, and I think something like 100 billion light years.
100 billion? Okay.
Yeah, you can double check me on that, but
I don't know. I didn't do that calculation. I know that the galaxy that I've been studying is about 5,000 million light years away. Yeah, but you have to think of a person also. Yeah, if you stretch it all out in one line, but it also gets stretched in this direction. Right?
Yeah, of course.
Yeah, but that would be
a thought experiment of what happens.
Yeah, it would be super far.
I also made the assumption of a room being 1 meter, just to simplify things.
Okay, yeah.
Small room. Yeah, so let's see, we do have a couple questions. Okay. Laura is wondering, how hard is it to find the FRB pattern inside all that radio data? How long does it take to find new ones?
That's a good question. So it is hard to find that radio pattern inside the FRB pattern inside all the radio data, because like I said, there's all that other interference happening too. But the fast radio bursts, so they emit a lot of energy, they're really bright, but by the time they get to us, they're actually fairly faint. They've traveled so far to that they're not super energetic by the time they get here anymore, right? But I don't know how long it, like, I don't actually know the process of searching the radio data for it. But I think, and how long did it take to find new ones? I think it's for the most part automated. Like there are algorithms and codes that we run to say, okay, we're looking at all this data and we're going to try to find a peak that's above a certain level, and this is going to tell us where the FRBs are. So I don't know how long that takes to run, though. I don't know if you know, Regina.
Yeah, I mean, I think, well, I was just thinking about how I would answer this. And one thing so FRBs have become such the hot new topic in astronomy. And so there are dedicated telescopes like the CHIME telescope that Georgia mentioned earlier that have been built over the past few years that are just now coming online. And these telescopes' whole job is to look for FRBs. And so sort of like Georgia mentioned, there's probably hundreds or thousands of FRBs going off every day. And it's just what we're limited right now is by our own telescope technology and, not being able to necessarily put telescopes all over the earth that can detect all of those. So there's a lot of them all the time, but it's just a matter of us not being able to detect them because we don't quite have, we have better and better telescopes now, but it's not worldwide.
Yeah.
Let's see. The next question is from Sarah, who's wondering, have spaceships encountered any issues with magnetar gravity, or are they too far away for us to even encounter that 600-mile radius?
Yeah, they're way too far away. So we know of about, I think it's about 30 magnetars that we know of inside our galaxy, but they are all way, way far away. I know that one that had an FRB detected from it, the one FRB that came from inside our galaxy was 30,000 light years away. So we're not getting there anytime soon. So we're pretty safe from magnetars.
Great. Let's see, Maya is wondering, do FRBs happen more on older or younger galaxies? And do you detect more on closer or further away galaxies? Really good questions.
These are great questions. These are things we're trying to figure out. So this is part of Alex Manning's work with the Hubble telescope images that I showed, where she found that a lot of the FRBs seem to be coming from spiral galaxies and on the arms of spiral galaxies. And these are, they're all fairly far away galaxies. I think there's been one from a close by, one from M81, right? That was close by. But I think they're kind of spread out. They're fairly well spread out. At some point, if they're too far away, we probably can't detect them. They're going to be too weak by the time they get here. So there's some, as we get better technology, hopefully we can get even further away ones. But there's some sort of a limit of how far away exactly we can detect them.
Yeah, and I'll just add that those are exactly the questions that we want to know the answers to.
Yes, those are exactly the questions.
Those are active areas of research.
There was an FRB conference this week, and those are exactly questions that people are asking and presenting on, trying to figure out.
Let's see, Rudy is wondering, do you see any rise or bursts in other parts of the electromagnetic spectrum, optical, X-ray, et cetera?
Yeah, so that's another thing that people are also studying and looking for. So as far as I know, there haven't been any very good detections of other wavelengths at the same time as FRBs. I know the one that was detected from the place of a magnetar also had X-ray emission, but other than that, there have been other surveys trying to catch in other wavelengths, but haven't really, as far as I know. It's also hard because most of the FRBs are single bursts and we don't know where they're going to come from ahead of time. So you'd have to be lucky to be pointing in the right direction to also be looking with other telescopes and other wavelengths and get that timing just right. But even in some cases where there has been the timing is just right, or we use a repeating burst to try to do that, there hasn't been other radiation detected.
And I don't know if you mentioned this, Georgia, but even our collaboration, our collaborators in Chile are doing this with optical. So, and tried to, with one of the repeating bursts, they tried to observe in the optical. I was reading the questions and I didn't hear if you mentioned this, Georgia. Did you, Alopeke?
Yeah, right. So that's one of the ones where they're using a repeating burst because we know it's more or less periodic, and so we can guess when there's going to be bursts and then try to look at it with an optical telescope at the same time. And there was we didn't happen, it was very thought out and planned, but looking at the same place as the FRB when a burst was detected by chime in radio, but there was nothing detected in optical.
Okay, the next question is from an anonymous attendee who's wondering if FRBs are proof of intelligent life in the universe because aliens have microwaves. A creative question.
Yes, great use of imagination in science. I don't think it's proof of intelligent life with microwaves in the universe. I think it's some other natural phenomenon because it's coming from everywhere.
Although I will also add to that, aliens were on the list early on.
Yeah. Alien light sails.
Yeah.
One of those.
Mm-hmm. Kate is wondering, what is your next step in your scientific journey, Georgia?
So I am, I'm still working on this research for a little bit, but my research fellowship ends this year. And so then I'll be moving on. Next year, I'll be going to graduate school in astronomy, and we'll be doing more science research then.
Okay, we have a couple more questions and I see one or two in the chat. So if you all want to hang out, we'll hang out for a couple more minutes and take these, if that's okay, Georgia.
Yeah.
Okay. So Rudy is wondering, is it possible that the low occurrence from our galaxy means the emission is directed out of our line of sight?
I don't know. Again, I think this is something that people are working on and asking, trying to figure out how, whether FRBs are sort of beamed in a certain direction, and then that could affect, like, if we only get to see it, if it's beaming in our particular direction. I don't know if, like, the evidence for that is that that there's a low occurrence in our galaxy. I'm not sure. I think that I know that the one that was detected in our galaxy was actually much weaker than any others that have been detected. So it was still the brightest radio pulse we have seen in our galaxy ever, but it was weaker than, like, the actual luminosity and the energy output of the object was significantly less than any of the FRBs that we've observed from all the other FRBs that we've observed from other galaxies.
Mm-hmm. Great. Let's see. The next question is from David, and he's wondering, how far away can you see magnetars?
How far away can you see them? That's a good question. I have no idea. Can you even? I don't even know if you can see them outside our galaxy.
Yeah, I also am not totally sure, but
yeah.
I suspect. I mean, most of the same for pulsars, you know, which
right.
are the same, are pretty much all in our galaxy that we can detect.
Yeah,
that we to do that in other galaxies.
Right. So the things that we know are magnetars, because they do emit, they emit, I think, in X-ray and in radio other times, like not FRBs necessarily, but other radio emissions and X-ray emissions. And those ones that like we've seen, I think we know about 30 in our galaxy. As far as I know, we don't know of any in other galaxies because they're too far away. So like Regina said, pulsars are very similar. They're the same base. They're also a neutron star, and they're also emitting in radio wavelengths and, like, shining radio beams. But they don't have quite as strong a magnetic field, but it's basically the same kind of object. And those we can only see in our galaxy, or I think there's a couple in the our like satellite dwarf galaxies, the Magellanic Clouds, but they're too weak to see from other galaxies. Like if they're that far away, we wouldn't get the signal.
Yes, and Max is wondering, are there any new exciting telescopes to detect localized FRBs being built?
Yeah, there are lots. Everybody wants to detect FRBs. So the Australian array that I was telling you about, the Australian Square Kilometer Array Pathfinder, it's actually the sort of precursor to a bigger array that's going to be amazing at localizing fast radio bursts and is going to detect way more of them also. So this is kind of the first test to see if it works, and we can see lots of, it's really good at it already. But the Square Kilometer Array in Australia, the SKA, is going to be a huge array of telescopes, radio telescopes that are going to do that. Chime also has a project where they're putting more, they're going to put more telescopes spread out over long distances in order to be better at localizing. So Chime's really good at just detecting fast radio bursts, but not great at knowing where they came from in the sky. But if you add in a bunch of more telescopes spread out, you can do better at localizing that. So I know of those two projects, but I know there's lots of other ones too. Yeah, people are really excited about fast radio bursts.
Great. Let's see, there's a couple in the chat. Somebody, Tim, is asking, saying that their son is part of the ADMX Axion experiment. What do FRBs have to do with dark matter detection?
So I think that's a good question. I'm not entirely confident, but I think that fast radio bursts are really not good at detecting dark matter because that dispersion measure, which is what we're using to detect the missing ordinary matter, is happening because of interactions with electrons. And electrons are ordinary matter and not dark matter. So dark matter, as far as we know, doesn't interact with light, and FRBs are light, which means that we are it's just going to go right through dark matter, just like all the other light that we see that goes right through dark matter that makes the dark matter so mysterious. So as far as I know, there aren't really projects with FRBs related to dark matter. There could be somewhere, but they're not super useful directly, at least because of light.
Let's see, and then there's a question from Pamela who's asking, how do you know if we are moving or they are? And I suspect maybe she means the galaxies.
The galaxies.
I guess that's what I'm guessing.
Yeah. So that's a good question. We're both moving. Everybody's moving. But yeah, so you use some kind of a reference point to decide what you're counting as moving towards and away, right? If you're talking about, okay, so two things. So one, if you're talking about within a galaxy, like that velocity map that's red on one side and blue on the other, and tells you how it's spinning, that you could anchor to some point in the middle and say, well, we're going to say that this point in the middle is not moving, and then see how much the edges are moving in comparison. But if you're talking about whole galaxies that are moving either away or towards us, we are also moving. The ones that are really far away, that are moving away really quickly because of the expansion of the universe, they're moving away from us and we're moving away from them. And so it's kind of the same measurement either way. Hope
Great.
That explains it.
Yeah. There's two more. Kathy actually just put a really great question into the Q&A. That is fantastic. And Kathy's wondering, if you can't see magnetars in other galaxies, how did we arrive at the theory that FRBs come from magnetars? Yes,
this is a good question. So we're still, looking for lots of evidence. We have not a whole lot of evidence, but one big piece of evidence is that the one FRB we have detected from our galaxy came from the same direction as a known magnetar. So we already knew there was a magnetar there and had already been observing it and learning about it. And then we detected a fast radio burst that came from the same place. And so we can kind of assume hopefully, sort of, that it came from the magnetar itself. That's only one though, so we're waiting for more. We're looking for other evidence. The other reason that magnetars are kind of on the top of the list is because, so they're super strong magnetic fields kind of get all mixed up and break, and this makes light get emitted. So we already know that they do this kind of bursting thing. And so it could be that sometimes they just burst really strongly to make an FRB. It also, I think it also, it helps explain the repeating and not repeating problem, where, so if you only ever detected FRBs happening once and they never happened again, it could be that there was something exploding, right? Something colliding, exploding, whatever, but it can't explode more than once. Like it can't blow up more than once. And so that kind of gets rid of that, at least for the repeating ones. Some people are still wondering if maybe repeating FRBs are caused by something totally different from single FRBs. Yeah, so people are still looking for things, but magnetars could do both. They could do multiple, they can do multiple bursts, but they could also have a single burst and then not burst again for a really long time, maybe. And we just haven't seen the other one. So magnetars kind of fit what we have so far. There is a little bit of, because the one that we detected from our galaxy was kind of a weird one, in that it was such a low, it wasn't super energetic, not as energetic as the other FRBs. That kind of makes us wonder about it. But we're waiting for more, looking for more evidence still. That's a good question though.
Let's see, we were getting lots of thank yous for amazingly enthusiastic and informative talk. And there's one final question that was put in the chat, which is, are FRBs only detected in active galaxies?
Active galaxies. Meaning like with an active black hole?
I'm not sure if Christina, who asked the question, wants to clarify. Go ahead.
What do you mean by active galaxy?
I think in general, we don't know the answer to that, even if it is an active black hole or active in terms of star formation. You know,
those are things we're looking for still.
Yeah, at this point, the jury is still out in terms of trends, you know, and that's something that
that's why we're making maps of host galaxies, is to see what kind of galaxies they are and what's happening in them, to try to figure out those kinds of patterns and trends.
Okay, I think that is about all of the questions. Yeah. I just want to thank you so much. And, you know, to your credit, Georgia, we've almost close to a half an hour over, and almost all of our attendees are still here. So
well, thank you all for staying and asking questions. I really appreciate it.
Yeah, this has been such a fun talk, and you did such a fantastic job explaining everything in a brilliant way. So I would just like to thank you for sharing all of this with us tonight. And of course, for being with us, being the research fellow and everything like that. I don't know what this year would have been like without you. So I just like to thank you for that. And to everybody who joined us tonight, thank you so much for coming. Next week, same time, same place, we will actually have the REU 2021 research presentation. So I would encourage you all to come back next week, and you'll hear a little bit more about FRBs, and then about a whole bunch of different research topics that our interns have been working on this summer. So don't miss it. It's also going to be great. Thank you again, Georgia, for everything.
Yes, thank you. This was really fun.
All right.
Good night.
Good night, everybody.
Bye.